in order to carry out this computation, we recall a very important formula that tells us how raising and lowering operators, J in general, for any angular momentum, orbital or spin, act on Jm states. And this is square root of J times J plus 1 minus M times M plus or minus 1 on J M plus or minus 1. And there's an H bar here. So this is how the raising or lowering operators on angular momentum acted. We've seen this formula some time ago. And we can use it, we can calculate a few things in order to warm up and be able to do our calculation more easily. What is, for example, J minus on a spin 1/2 state? If you lower it, you must get something proportional to 1/2 minus 1/2. Let's just get the number. So here you have square root of 1/2 times 3/2 minus 1/2. And we're doing the minus, so 1/2 minus 1 is minus 1/2. And here is the state 1/2 minus 1/2. So this is 3/4 with the 2 minus plus 1/4, that's 1. Square root of 1 is 1. So this is very simple. It's just H bar times the 1/2 minus 1/2 state. That's kind of a neat thing. If you lower the state 1/2, 1/2, you just get H bar times the state below. Another one that is maybe useful is what is J minus acting on the state 1, 1. That's another top state of a multiplet of angular momentum 1, so you should get something with a 1, 0 here. And you have an H bar square root of 1 times 2 minus 1 times 0, because it's M, which is 1 minus 1. We're using the lower sign on this expression, times the state 1, 0. So this is nothing else but H square root of 2, the state 1, 0. Okay, so these are a set of practical equations. And now we begin our identification of the states. So we're looking for a multiplet of spin 1, and we identified that this is the state with m equals 1. So this must be the state with spin 1 and m equals 1. These are labeled for total angular momentum. You see, in a multiplet of spin 1, there's only one state with m equals 1, there's only one state with m equals 0, and there's only one state with m equals minus 1. So here is the only state with m equals 1. So this state must be a state with total angular momentum 1. So this state is the state 1/2, 1/2, 1, tensor 1/2, 1/2, 2. Very nice. The other state, the 1 minus 1, must be the state 1/2 minus 1/2, 1, tensor 1/2 minus 1/2, 2, because it's the only state in the tensor product that has m equals to minus 1. The only question now is which is the state with m equals 0, and here we have a problem. These two states have m equals 0, so it's one linear combination of these two states that must have m equals 0. So we have a simple strategy for doing this kind of calculation, and it's to use the lowering operator on this state to find what 1, 0 is. And well, the lowering operator will act on the left and it will also act on the right, and hopefully it will give us the answer. So let's do that. So let's act with the lowering operator S total minus on the state 1, 0, 1, 1, I'm sorry. And that will be equal, if you wish, we can write this in detail, S minus of the first Hilbert space, 1 plus 1 tensor S minus on the second Hilbert space, on the right-hand side, which is 1/2, 1/2, 1 tensor, 1/2 minus 1/2, 2. Okay, so this operator is the same as this. This is suitable for acting on 1, 1 in the total angular momentum, and these operators for the first Hilbert space and second are natural to act on the right-hand side. So if we act, we should get an interesting thing. Now, the lowering operator on the 1, 1 was calculated before, so it gives us h square root of 2, the 1, 0. Great, this is what we want. Now, this operator is going to lower, act on this state, on the 1/2, 1/2, because it's the first one, and nothing on the second. It's going to give you something. So what is that something? S minus on 1/2, 1/2 is h bar 1/2 minus 1/2, 1, and nothing on the second. So tensor 1/2, 1/2, 2. And then the lowering operator here, the second one, will give you plus another h bar. The first state is not changed because the identity is acting on it. 1/2, 1/2, 1. But the second is changed because S minus 2 is acting on this second one. So I'm sorry, I copied something funny here. The 1, 1 state has both states with a plus. And everything is so far so good. So S minus acting on 1/2, 1/2 would be the h bar 1/2 minus 1/2. Now we can cancel the h bars. The square root of 2 can be put on the other side. And now we have an answer. I'll write this state first. So I'll write this answer as the 1, 0 is going to be 1 over square root of 2, sum of two states, 1/2, 1/2 tensor 1/2 minus 1/2, 1 and 2, plus 1/2 minus 1/2, 1 tensor 1/2, 1/2, 2. Close parentheses, and we can box this equation. Now we have the full multiplet. We have the 1, 1 state, the 1 minus 1 state, and the 1, 0 state. These three states are the states that correspond, this is an important equation as well, correspond to the multiplet with spin equals 1. What is left at this moment is to identify the state that corresponds to the other multiplet, the singlet. So there must be this linear combination of the two states with m equals 0 belongs to the multiplet with spin equals 1. some other linear combination must belong to the multiplet with spin equals 0. Now, this other state is the state 0, 0, and must be a linear combination of these same two states, and it must be orthogonal to this one. Why should it be orthogonal? Because these two states are eigenstates of a Hermitian operator, S squared, and have different eigenvalues. And you know that two states that are eigenstates of any Hermitian operator with different eigenvalues are orthogonal. So this is guaranteed. However you build this state, it should be orthogonal to this one. So the orthogonality will be true, will hold, if you simply change the sign, the relative sign between these two terms. So I claim that if you put a minus instead of a plus, you will get an orthogonal state, a state orthogonal to the 1, 0 here. So I copied the same state and just changed the sign, and I claim this is the state 0, 0. Now, you could test the orthogonality. It would not be difficult. I'll say maybe a few things about it. Maybe we should do a little of that to make sure you understand how the orthogonality works. I'll do it on this blackboard. So I will write the bra 0, 0. And it's 1 over square root of 2. Any number should be complex conjugated. And now I will simply turn these two kets into bras, but leave the tensor product. So I'll have the 1/2, 1/2 of 1 tensor product with 1/2 minus 1/2 of 2 minus 1/2, 1/2 of 1, no, 1/2 minus 1/2 of 1, tensor product with 1/2, 1/2 of 2. You should notice that these states came out with the right normalization. In fact, this state is well normalized. This is orthogonal to this. If you take the bra and you hit into this, it just is orthogonal, because in the first Hilbert space, you will have, for example, the 1/2 state hitting the minus 1/2, and that's 0. So they're different enough that these two terms are orthogonal. So the 1 over square root of 2 is such that the norm squared of this vector is equal to 1. Here, we've produced now the bra, and you could do the bra and act on this ket. Now, the first term here would hit the first term there, and it would give you a factor of 1, because they're appropriate. The m's are well coordinated. On the other hand, the first term there gives 0. When it hits on this vector, the m's are opposite. So you get from the first term there and the first term here, you get a factor of 1. And from the second term there and the second term here, because of the relative sign, you get a minus. So indeed, it is true that 0, 0 is orthogonal to 1, 0. And that is sufficient evidence that this state must be the singlet state. You could do more tests on this state. For example, you could try to race it by acting with a total racing spin, or lower it, and in both cases you should get 0, because this is a state that can't be raised or lowered. It has 0 angular momentum. Now, this notation for these 4 states, in principle, we're done here. We've obtained the 4 states that represent this tensor product, 4 states, one as a triplet, 3 states that go into the triplet, and 1 with a singlet. So we're done, but this is cumbersome writing, so we'll try to write it in a briefer way. To do that, let's streamline our notation, in which something like 1/2, 1/2 will be represented simply as an arrow up, and 1/2 minus 1/2 would be represented as an arrow down. So let's do that. In that notation, we would have that the state 1, 1 would be arrow up for the first Hilbert space, tensor arrow up for the second Hilbert space. A little briefer already than the equation we're copying here. The 1, 0 state would be 1 over square root 2, arrow up for the first state, arrow down for the second one. 1, tensor arrow down for the second, plus arrow down for the first, tensor arrow up for the second. Finally, you have the 1 minus 1 state. That would be written as arrow down and arrow down. Arrow down for the first, arrow down for the second. We could also do this for the singlet state, but let's simplify even further the notation. It's still writing too much. So whenever you have an arrow up and an arrow up here, we'll just put something with 2 arrows. You'll know the first arrow represents the first particle and the second arrow the second one. So we'll go briefer still, and we'll write the 1, 1 state as arrow up, arrow up. You know the first arrow refers to particle 1, the second to the particle 2. The 1, 0 state will be 1 over square root of 2, up, down, plus down, up. The 1 minus 1 state would be 2 down arrows. And the other state, our singlet, which is many times a very useful state, the 0, 0, would be 1 over square root of 2, up, down, minus down, up. So this is probably the way people remember this. It's a relatively nice notation. You do away with this tensor products. You put the arrows one after the other. It's fairly self-contained. And here you see the individual spins. And here is the labels of the total angular momentum. So we've performed the addition of angular momentum. The whole addition of angular momentum really meant reorganize the basis of the tensor product from the naive basis, which is just the direct products of all the bases of one vector space to another vector space, find a new basis in which the total angular momentum operators act naturally, and tell the answer of this problem is to tell what kind of angular momenta appear for the total space. So you started with two spin 1/2s, and the angular momentum that appear were spin 1 and spin 0. So we will want to do, in all generality, understand when you tensor product vector spaces carrying certain representations of angular momentum, what representations of angular momentum, of total angular momentum, appear in the tensor product. So this is the addition of angular momentum for the simplest case.